The macro world. We live on the edge of an average galaxy, but even so, its dimensions are bigger than anything we can imagine. It is 100,000 light years across. Lost somewhere among these stars, there is our solar system. Its size is about 10,000 million of kilometers. Our Earth is one of the smaller planets of the system. Our everyday life happens at small dimensions, and so it now seems that here we have returned from our journey into the unknown. But there is still another mysterious world, the micro world. We explore its frontiers using microscopes. Somewhere, at a very small scale, there is something which the ancient Greeks named the atom. An atom is extremely small. It is 10 to the minus 10 meters across. It is hard to imagine, so let's use an analogy. A grain of sand is so many times smaller than the Earth as the atom is smaller than a grain of sand. Atom in Greek means something impossible to divide. The Greeks thought that atoms could not be divided into smaller pieces, but they are the most basic elements of matter. At the beginning of 20th century, Joseph Thomson imagined an atom as a kind of cake. In such a cake, the electrons would be as raisins, small and light. The nucleus of the atom was discovered by Ernest Rutherford. He directed a stream of so-called alpha particles onto a thin foil of gold. On the other side, he installed a screen covered with a substance which shines when it is hit by an alpha particle. According to the Thomson model of the atom, all alpha particles, without any difficulties, should go through the gold foil and then should hit the screen. So one would expect that the screen would shine. However, something surprising happened. The screen was shining, but some of the alpha particles didn't go through the foil. They seemed to deflect from the atoms. Rutherford wrote, "It was the most unbelievable event which ever happened to me. Nearly as incredible as if you shoot a 15-inch bullet into a sheet of paper and then the bullet deflected backwards and hit you. How can this be explained? Of course, the heavy alpha particles could not be deflected by the electrons because the electrons are so small and light, like butterflies. A flying bullet cannot be deflected by butterflies. So by what? By this cake?" Rutherford concluded that there is no cake. Instead, there is something tiny, but very massive. Something that lies on the center of the atom. This something he called a nucleus. And so he conceived a new image of the atom called the Rutherford model. Today we know that the atom consists of something. The atom has a structure. The atom consists of a central nucleus with the electrons orbiting around it. However, this image you see is not true. The scale is not accurate. If we draw an atom so that the nucleus is as big as an apple, the electron should be drawn 10 kilometers away. Between them, there is a huge, empty space. Almost all of the mass of the atom is concentrated in its nucleus. Electrons weigh almost nothing. They are like butterflies flying around a heavy iron ball. If we throw away the electrons and the empty space and build matter not of atoms but only of atomic nuclei, we would create extremely heavy material. A dice made of such material would have a weight of 140 million tons. In comparison, a dice made of lead would only be 12 grams. Since nuclear matter is so extraordinary, let's look closer at the nucleus. A nucleus also consists of something. We say it has structure. An atomic nucleus consists of protons and neutrons. According to the number of protons in a nucleus, we have a particular chemical element. For example, a nucleus of helium consists of 2 protons and 2 neutrons. Here are other examples of nuclei. What would happen if we try to combine 2 such nuclei? As a result, we would obtain a new nucleus consisting of the combined protons and neutrons. It would be a nucleus with 79 protons, a nucleus of gold. So we have learned a method of producing gold from 2 lighter elements. Unfortunately, such a combination is not easy because the 2 nuclei repel one another. So we have to collide 2 nuclei in such a way that they will not deflect like 2 billiard balls, but combine like 2 drops of liquid. The collision will take place in a vacuum. A projectile nucleus will hit a target nucleus. Here is a target chamber. The nucleus will gain a high speed thanks to a device called an accelerator. This is the path of a projectile nucleus. A projectile nucleus comes from the accelerator. The situation is repeated many times. This is the view seen by the projectile nucleus, flying through a beamline as it approaches the target chamber. As we see, the expected combination of 2 nuclei has occurred. The result is a new nucleus, the so-called recoil nucleus or compound nucleus. The reaction itself is very fast. The nucleus created by this reaction is now flying to a special detector. This is the so-called recoil filter detector built in our laboratory. It consists of 18 smaller detectors, which are all able to detect the production of a particular nucleus. Let's concentrate on the reaction. From the accelerator comes the next projectile nucleus. Let's look closer. Too fast. Let's stop the frame. The projectile nucleus just before hitting the target nucleus. collision. Two nuclei combine like two drops of liquid. As a result, we have a so-called compound nucleus. Part of the energy of movement of a projectile was converted into excitation energy of the compound nucleus. This is symbolized by the glow around it. The compound nucleus would like to reduce its excess of energy. Figuratively, it would like to cool down. It can do this by emitting an alpha particle, a proton, or a neutron. It can also emit a gamma quantum. Quantum in Latin means a portion of invisible electromagnetic radiation similar to X-rays. Gamma quanta can have different energies. Here they are marked by using different colors for each quantum. One is red, the other is yellow. The emission of gamma quanta takes away the rest of the excitation energy from our nucleus. Gamma quanta are emitted in different directions. To register them and to measure their energy, we surround the position of the reaction by a system of detectors for such radiation. These detectors are able to measure the energy of the gamma quantum which hit them. The system of such detectors is like a group of microscopes watching the position of the reaction. This is how such device looks in reality. This is a system of germanium detectors. This is what the whole measuring hole looks like. The device is called Garel+. We saw here the detectors surrounding the position of the reaction only from one side. It's easy to imagine the other side. This is how the famous Euroball is built. Now let's think how the detectors are detecting the gamma radiation. Do you remember what a diode is? A diode is a device which conducts electricity in only one direction. If we put the voltage so that plus is here and minus here, the electric current will flow through the diode. But such a situation is not interesting for us. Let's change plus and minus. The electric current can't flow. But if a diode is hit by a quantum of gamma radiation, it creates electrons and holes in the diode. This will cause a pulse of electric current to flow. Notice, the size of a pulse will depend on energy of the gamma quantum. This is very important. Not only do we detect the gamma quantum, we are also able to measure its energy. So the gamma quantum we detected is converted into a pulse of electricity. The bigger the energy of the gamma, the bigger the pulse. Using an analog to digital converter, we can convert an electric pulse into a number of range 0, 4095. The bigger the pulse, the bigger the number. Let's summarize. The energy of a gamma quantum, its color, at first was converted into electric pulse and then finally into a number. So now its energy or color is described by the number. Since we now have a number, we can use the computer to do the rest of measurement. This is a scheme of a measuring system. The position of the reaction is surrounded by the detectors where gamma quanta will create pulses of electricity. The electronic devices which form these pulses and finally convert them into numbers. The computer which collects these numbers. In the computer there is a special program which remembers how many times during the measurement we registered gammas of a particular color. Here is the example. in the memory of a computer, there is something like many compartments dedicated to the quanta of different energies. Now, if the computer registers a number of 14, the computer will remember this fact in the compartment number 14. If the number 25 arrives, the computer remembers this in the compartment number 25. If the number 14 arrives again, the computer again remembers it in the compartment number 14. Now it knows that there were two events of observation, the gamma with energy 14, and so on. During the long measurement, the table will fill up step by step. As a result, we will have a plot telling us how many times during the experiment we registered the gammas of particular energies. This kind of plot is called a spectrum. What can we read from it? For example, that during this particular experiment, the most frequently observed quantum was that with a color of 19. With an energy of 19. Also, very often we observed quanta with energy 14. However, there was no quanta with energy 16. Let's imagine that we draw a white outline on this plot. We obtained something that looks like a New York skyline. This is how it looks on the computer screen. We can read here which gamma quanta were registered during experiment. A spectrum is characteristic to a particular nucleus. Different nuclei have different spectra. Looking at spectra, we try to investigate how a nucleus is built, what structure it has. That's why we are the laboratory of the structure of the nucleus. Since we do this by looking at spectra, that's why our department is called a nuclear spectroscopy department. Actually, by now you know almost everything. You could still ask, who is the man on this photograph? Let me explain. Here is Joseph Thomson. This is his student, Ernest Rutherford. And this is Henryk Niewodniczański. As a young scientist in year 1934 and 1935, he worked under the direction of Rutherford. Henryk Niewodniczański in 1955 created our institute. He was its first director and the head of our Department of Nuclear Spectroscopy.